Good afternoon, everyone. We are here to talk about the U.S. solar energy roadmap for next 10 years. My name is Wendy, and I will first start our presentation with the solar market background and technology. Then Ben will present the interesting pricing info from the economic standpoint. Kai will speak about the distributed solar generation, and Mariam will look at the solar energy from the environmental aspect. Finally, Hira will talk about the importance of solar-related policy for the next 10 years in the U.S. First of all, I would like to let you all know that year 2013 was a record year for the U.S. solar industry. U.S. installed 4,700 megawatts of PV last year, up 41% over 2012, and nearly 15 times the amount installed in 2008. We also installed 410 megawatts of constant solar power last year, increasing the total CSP capacity by 75%. In fact, more solar has been installed in the last 18 months than the total from 30 years prior. There is a total of 12.1 gigawatt of PV and 918 megawatt CSP operating in the US today. So let's compare the US market to the global market. The world's cumulative PV capacity has surpassed 100 gigawatt in 2012. The US development for both PV and CSP technologies appears to follow the global trends. However, although CSP has already started in the 1980s, it has no additional capacity added until 2006. Also, even though the growth rate of the solar industry has been very encouraging for the last couple years, currently it only accounts for 0.2% of the global electricity production and only 4.7% of all renewable energy. Let's turn our focus to the technology. The PV market can be classified into two main categories: crystalline silicon and thin film technologies. Currently, 85 to 90% of the PV market is dominated by the wafer-based crystalline silicon technology, the most conventional type of solar cell, and therefore it is commonly referred to as the first-generation technology. However, the cost of the silicon wafer is very expensive. In order to reduce the cost for the solar cell, we can make the solar cell thinner. And therefore, the thin film technology was invented and is also called the second-generation technology. One of the most important thin film technology is the cadmium telluride, CDTE. It attracts more attention in the US because we have the world's largest thin film PV module manufacturer, First Solar. There are two types of CSP technologies available in the market. The first type of the CSP technology is the parabolic trove collector. This system uses a parabolic curve, trove-shaped mirrors, and single-axis tracking to follow the sun and focus the sunlight onto a receiver tube. A heat transfer fluid circulates in the tube, absorbing the heat, and then transfer the thermal energy to a turbine for electricity generation. There were 9 parabolic trove plants built in Mojave Desert in California back in the 1980s for the Solar Electric Generating System project. It was the largest CSP plants for almost 3 decades. The second type of the CSP technology is the solar power tower, also referred to as the central receiver or the heliostat collector. This system utilizes a field of mirrors called heliostats, which individually track the sun on 2 axes and redirect the sunlight to a receiver at the top of the tower. The heat transfer fluid in the receiver can be heated up to 1000 degrees C for steam generation. Solar tower has a high operating temperature and hence a high efficiency than parabolic trove for CSP technology. And we currently have the largest solar tower plant in Mojave Desert, California. This picture is showing 3 solar plants built for the Ivanport Solar Electric Generating System project, which began commercial operation in December 2013, and it has a total capacity of 377 megawatts. For the PV technology, the learning rate is around 20%. The manufacturing price for the PV module has dropped almost 50% from year 2008, and now is sitting around 55 cents per watt for crystalline silicon and 59 cents per watt for CDTE. It is expected to further drop down to 40 cents per watt by year 2018. The average efficiency of the PV module will also increase to around 20% in next 5 years. This is only the manufacturing price per watt, and Ben will have a lot more details for the installed price for the solar market. However, there's a different case for the CSP technology. The learning rate is just around 11% because CSP is still at its infancy stage. The manufacturing cost for the CSP system is still very high. As a conclusion from the technology standpoint, crystalline silicon will still dominate the solar industry for the next 10 years. But CDT technology will definitely have a larger market share in the US due to the excellent improvement in cost reduction and efficiency. Both PV technologies can be further stimulated by policies such as a better pricing policy and a more sensible interconnection policy, which Kyle will talk more in his section. Also, the strong initial increase in the CSP capacity back in the 80s was a result of the notable federal and state tax incentives. However, there was no additional capacity added until recently. In order to help the CSP technology growth, we will need solar policies such as R&D funding and solar investment tax credit, which Hira will have more details in her section. Combining with the solar policies, US will definitely produce more solar electricity in the near future.
One of the major contributors to the success of photovoltaic is the economics associated with such systems. As technological advances are made, the price for these products will decrease. Despite this, the cost of electricity generated by PV compared to current prices is what really matters. The graph here was generated in MATLAB from U.S. Energy Information Administration data. The graph depicts the current cost of electricity in cents per kilowatt hour across all states for the residential, commercial, and industrial sectors. As can be seen, the current cost varies considerably between states, making national PV objectives that much harder. The average residential rate is currently sitting at 12.6 cents per kilowatt hour, while the high is 36.99 cents in Hawaii, and Washington with the low of 8.6 cents. The cost per kilowatt hour, though, is not the only thing that we should be looking at, but rather trend data. So this graph depicts the average retail price for electricity across the three sectors with the same units displayed over the past decade. As can be seen, the cost has increased by approximately a third since 2004, and there has been a constant increase from 2004 to 2008. Then with the economic downturn, cost per kilowatt hour leveled out from 2008 to 2013, especially for the commercial and industrial sectors. According to the U.S. Energy Information Administration, costs have increased 1.6% for residential, 5.6% for commercial, and 7.9% for industrial from 2013 to 2014. The last two slides of data was meant to give a baseline for the cost of electricity in the U.S. Now again, the only way the majority of customers will make the switch to PV and renewables in general is if the cost per kilowatt hour of electricity generated by PV is competitive with the cost sold across the U.S. This graph was generated from U.S. Department of Energy data and is categorized by generating capacity of PV systems. You have less than 10 kilowatt, 10 to 100 kilowatt, and greater than 100 kilowatt systems. Considerable variation was not only seen between states, but also within each state. The median installed price, including all associated factors for installation in dollar per watts, is plotted against a sample of states that had enough data points to be represented. Likewise, breaks of data are due to a lack of data for a particular size system within a particular state. Minnesota, for instance, does not have enough greater than 100 kilowatt systems to generate a meaningful average. They may actually have none. Of note, California is not the cheapest, while Colorado is very competitive. Here, costs in dollars per watt for PV installs and capacity, sorted by state, is represented. The left y-axis in blue shows the average cost in dollars per watt for PV installs across each state. The variation in this data versus the last slide is mainly due to when the data was drawn. The last graph was from 2012, while this data is a couple months old. The right y-axis shows the capacity in total megawatts for all PV installs within each state. By plotting the data together, I was testing to see if capacity and cost are related. They are not. California has a significantly higher capacity than any other state, but is still middle of the road as far as cost. Prices for installed PV systems have continued their decrease over the past decade and a half, as can be expected. This trend should continue, especially as technological advances, PV policy, and incentives are provided to reduce costs to the end-use customer. Specifically, installed prices have decreased approximately 6 to 7% per year, and then from 2011 to 2012, installed prices fell by approximately 14% for systems less than 10 kilowatts and systems 10 to 100 kilowatts, and 6% for systems greater than 100 kilowatts. According to Navigant Research, installed PV prices will continue to drop at a rate of 3 to 8% per year to reach a global average cost of $150 to $219 per watt by 2020. Net generation of electricity from solar is split up by states in this graph. You can see the blue line represents 2013 with the green 2012. Of note, we've increased from one year to the next, which is good. Additionally, not surprisingly, California and Arizona are two states with the highest electricity produced, along with significant increases in percentage. According to the EIA, electric generating capacity of PV systems at the end of December 2013 reached 4,978.3 megawatts. Over the next 12 months, an additional 2,697 megawatts will be added in capacity across the U.S., providing a total of 7,675.3 megawatts of electric generating capacity by December 2014. Again, we have more numbers for you. In this case, the levelized cost of electricity aims to break down the many factors that contribute to the cost per megawatt hour between different sources of electricity. As you all know, by doing this, we can generate a much better overall comparison. I apologize for the eye chart on the x-axis, but conventional fossil fuels are generally on the left with the renewables on the right. The box plots show the average levelized cost with the red lines and then the minimum and maximum costs. The costs are based on a 30-year cost recovery period and include the levelized capital costs, fixed O&M, and variable O&M to include fuel. The variations between min, max, and average cost for each source are due to factors such as varying policies, technology, and incentives in different regions of the U.S.
When it comes to solar power as a distributed energy resource, it becomes particularly necessary to appropriately value the benefits that it provides to the grid in order to properly incentivize its growth. The status quo in regulated markets for pricing PV is an antiquated policy that currently values PV no differently than other distributed generation resources. This comes from the Public Utility Regulatory Act, which was passed during the 70s, which was the first act requiring utilities to purchase generation at a price equal to the utility's avoided cost. This cost is made up of various costs avoided due to not having to produce that marginal unit of electricity, not having to have infrastructure upgrades or maintenance or capacity upgrades, but it does not distinguish between types of distributed generation, and therefore the various benefits of distributed PV are not appropriately valued. The various benefits of distributed PV can be divided into two subcategories, first being the temporal benefits, and that is first of all, the time coincidence with peak load during the day and the peak output of the PV, as well as the time coincidence with higher load during the year, i.e. during the summer when people were using their AC, and higher outputs of PV, which tend to be slightly higher during the summer with some peaks during late spring and early fall depending on the orientation of the panels. The second subcategory is the spatial benefits. Distributed PV and distributed generation in general can help alleviate transmission line congestion. It can decrease distribution system line losses out on the distribution feeders, and it helps improve voltage stability and therefore grid stability overall. If we look at some sample data from ISO New England, which is an average per customer for 2011, and some generation data created with NREL System Advisor model based on a 6 kilowatt residential system, you can clearly see the correlation between generation here in red and consumption here in red. Not every distribution feeder is created equally. Due to congestion, line losses, and nearby generation on the transmission system where that substation happens to be, there can be marginal electricity prices that vary greatly across different regions. You can see here in the table at the bottom, I'm showing 3 different zones in New York ISO. This is the average real-time price, locational-based marginal price in 2011. And you can see there's nearly a 50% difference between the lowest and the highest LBMP. That's the difference between New York City and North. And that's basically a market indicator reflecting the marginal cost of providing an extra megawatt hour of electricity in New York City and North. Combining those differences with the fact that there's a 20% difference between the average on and off peak LBMP, on being when PV is outputting at least 50% of its yearly max, you can see that there are a lot of intricacies that go into appropriately valuing an extra unit of distributed generation. If we overlay this locational-based marginal price data with the data from 2 slides ago, we can see the coincidence with high demand translated to a coincidence with high marginal price. And we can see that coincidence with the high PV output. This chart does a particularly good job of showing why PV cannot be valued the same way as other distributed generation, and combining this with the spatial considerations from the previous slide really shows a need to revisit the way distributed PV is priced in order to appropriately incentivize its increased adoption. PV systems today are connected to the grid in accordance with the Energy Policy Act of 2005, which essentially adopted IEEE's 1547 standard as the national interconnection standard. This standard includes stipulations such as frequency trip-off and a lack of voltage regulation by the inverters, and essentially boils down to the PV not being as beneficial as it can be and being, quite frankly, pretty dumb relative to its full potential. But this does not negate the fact that the basic relation between demand and PV output merits a more appropriate valuation. However, in 2018, there is a planned overhaul of IEEE's 1547 standards, which will allow a lot of these PV and inverter benefits that will help the grid, including more voltage and frequency regulation, inverter communications, microgrids and islanding, all of which will improve grid stability and decrease outages, truly leading to a smarter grid. Essentially, as distributed PV generation continues to grow and as we seek to continue to incentivize this growth, it will be important to appropriately value PV in accordance with the benefits that it provides to the grid. With markets becoming deregulated, public utility commissions should seek to compensate PV owners fairly and fully, and this will help to further incentivize its growth. And going forward, policymakers and stakeholders such as IEEE need to make sure to adopt sensible interconnection policies, ones that will allow the full potential of PV to be realized on the grid. And as we continue to do that, along with deregulation, there's going to be a need for an iterative process of appropriate valuation for these distributed generation resources.